Okay, try just to make sure that my diagram makes sense.
All right, the warm-up, what's the answer?
Wait, I'm not there yet.
It is 1.
I can't tell you.
I need for
Ian, sit down, man, sit down. Your chair. Your chair, I said.
I have no chairs that I own in this area.
Well, that's true, but the one that has your stuff at it.
Challenge accepted. Let me just undo this over here. Oh.
All right, let's quickly answer the warm-up. Everyone has a quick solution for the warm-up. What's your quick way in on this problem? Or let's first name a slow but correct way to do it. What would the slow but correct way to do it be? Yeah.
Find sum of x and then find sum of y and then subtract.
Correct. Both of those are sums you know how to find. They're easy arithmetic series. The one chore would be figuring out how many things there are in the list, right? It's not too bad. How many things are in each list? If you care. How many things are in each list? What did you say?
Wait, why did you apply That's true, it's 46.
45, 46. Okay. All right, what's well, all right, now, so that is a way to do this. What's the faster way? Okay, Cam.
Yeah, I was just going to say, you count how many terms there are. Did you know both sequences have the same common difference? You know that each term is going to have, and based on the relationships between the first three numbers in the series and the last number, you can tell that each series, or each of the terms in y is 10 more than each of the series in x. So once you find the amount of terms there are, you can just multiply that by 2, and that's your answer.
Oh, okay, so you're saying, yeah. So now, Cameron has a nice, fast way to do this. He says, if you subtract these series just term by term, you get 2 plus 2 plus 2. So it's 2 times, that does sound like a much faster way. 2 times however many terms you said there are. Someone have an even faster way. I know, you said the wrong answer.
I know.
Yeah, and I was so shocked.
I'm dumb sometimes.
I guess I'd like to have you pair up other things in these lists, right?
Oh. Oh. Never mind.
Maybe just kind of tilt your focus. You know.
Yeah, if you just shift it over one.
If you shift over one, what happens? Or what?
You get like 12 minus 12 and then 14 minus 12.
So you notice that all the terms in this cancel when you do this minus this. Yeah, all the terms from this cancel except for 10. So what's the answer? 92. Boom.
Wait,
So how many? 100. It's this thing minus this thing. So that means all these go away, and you have 102 minus 10, which is 92. Where was that problem taken from?
my IA.
Where was that problem taken from?
The internet.
Some dude's brain at some point.
SAT.
Come on, no.
Actually landed right as the human brain didn't come up with it. The supercomputer that
You should recognize
The
it.
IB problem.
It's a test that many of you took. The AMC. If you didn't take it this year, you should take it next year. It rewards elegant mathematical thinking. So, all right. No, that wasn't on this year's AMC. All right. Let me just hear where we're at here. Let's see. We have a test on Tuesday, scheduled for Tuesday. The IB problem yesterday went fine. I told you it wasn't going to be too bad, right? I mean, it's interesting. They're interesting. They were all HL problems, you know, from the HL test. But none of them had to do with infinite series infinite non-arithmetic geometric series. So I think you were okay probably on that. The test is scheduled for Tuesday. We're going to, I think, move that to Wednesday now.
yeah.
So just to give Bias a little more time to clean up from induction and do the review and stuff. So yeah.
Thinking a little bit more ahead. Can we push it to Thursday because of the fire drill?
The cumulative. We're gonna not have like a cumulative test per se. We're
What are we doing?
gonna do something though else.
Wait, so what are we doing after we have a bunch of cards?
We're gonna take an a sample IB test. I have a box over there with your names on it. So we're gonna take. That's one thing we'll do among others. But
For like third grade.
we don't have a festival of knowledge in the same way we did last time. All right. I will make you do some more challenge problems sometime here. I'm trying to think when I need you to have them. I'd like you to have them be thought about on Monday and Tuesday as well. So I don't know when we'll assign some more at some point here. Maybe Monday night you'll have I'll assign a handful more. Huh?
For the challenge problems, answers to the challenge problems.
Yeah, I'll put them online sometime.
Like today?
No.
Tomorrow?
No. Maybe on Tuesday. Okay. Well, the one topic we do need to cover, that we're going to cover to round out this unit, is mathematical induction. There's one other homework that is on the sheet that we're going to skip this year, called Taylor series. So, but that's okay. You'll get it really hard next year in PC Calc.
Okay.
What?
You're thinking like, I mean, I'm glad it's just the computer, but
What's that?
the Taylor series.
Yeah. What about
I
it?
want it harder next year.
Oh, well, no. I meant you'll learn it next year. But
Okay.
we could do it as a bonus topic, maybe. I don't know. I'll give you. I have it all copied. I could give them to you just for fun. You could do that. I will do that. I'll just give them to you as an optional thing that you can do too. Okay. All right. This is the statement that I showed you outside just a minute ago, and it is somewhat remarkable if you haven't thought about this particular fact before. And there are a number of ways to prove it, many of which are already accessible to you, and maybe you have even a geometric proof of it, perhaps, or some other proof. You could use it. You could use a thing we had from earlier this year, actually, too. What kind of series is that? It's actually an arithmetic series, so you could actually use the arithmetic sum formula, and you'd be able to prove that pretty quickly. Just you push some symbols around, and you get n squared. Ian, you want to explain your work quickly?
If you have a case of 1, then you have 1. 2 squared, you get an additional 3 on top of that because 2 times 2 is 4 minus 1 is 3. You add that to the previous one, you get 4. Do the same for 3, you get 5 plus 6 plus 1 is 9. 4, you get...
Well, you got to slow down. People don't understand. So, really, you need like an animation for this picture.
Yeah.
So I think he's saying that, is it clear that you have a square, you have 1, if you add up just the first number 1, you get a square. These should be like squared or something. The area of that square is 1. And then if you go to the next biggest square, which is 2 squared, isn't that clearly, you did it in blue and black, but from your perspective they might look the same. Is it clear that the next layer is 3 more? And that's a square of size 4, obviously. And then the next layer, you're adding the next odd number, the third odd number is, and it's clearly 2 bigger than the previous number. You just added 1 to each side. So he's saying the next odd number is 5, and that makes a square. And then as you add odd numbers, you get these L shapes being added to like layers, and you get a square. So that's a nice, like really kind of proof without words almost. Like that's convincing enough that I'm like ready to walk away. But we'll use this as just kind of a toy example in our first encounter with a new proof style called mathematical induction, which is good because we already have like a pretty fully aware that this seems true, and we have a couple other ways to prove it, and then we'll provide some other things that are a little more challenging that induction will help us with. So here's how a proof by induction works. There are 3 steps to every math induction proof. If you're saying as a mathematician in the mathematical community that you're going to like prove something by induction, that every mathematical listener who has had their education in mathematics will expect the following 3 things to next come out of your mouth. First, you verifying that it's true for whatever the initial case is, or the base case. Sometimes that's 0, in this case, or it's 1. Like, is it even true for 1? Now here it's silly to even say that, right? Is the sum of the first term 1 squared? Yes. Done. Sometimes it's a little trickier, but it's always not a huge issue. Well, I shouldn't say that. is generally easy. And so you might be even thinking, like, why is that necessary? The next thing that you'll do in a math induction proof is just assume that it's true for some generic fixed k value. So let's just assume, for the time being, again, this is a huge assumption, it could be wrong. Let's assume temporarily, not that it works for all n, that it happens to work for some k. There's some particular value that it does work for out there. Call it k. Is that okay? That's why the name changed. And then final step, and see if then the next thing to do is to figure out, well, really, Mr. Chase, does this constitute a proof? And I think you'll see that it does if I can explain it properly. The last step, and maybe the most important step, is the inductive step. And that's prove, given the previous things, that it's true for the next case. So what you'll have done, if you do this properly, is you'll have constructed a proof, you'll have established, the Promethean board is not calibrated, that's going to be a little bit of a problem. You've established that it's, that, like, if the statement is called P, if our statement is P, then you've established that statement P is true in the case that n is 1, right? You just check that. You assume that it's true for some k value, assume that's true, and the thing you're going to assume, and then the thing you're going to prove is that given that P of k is true, that it follows that it must be the case that P of k plus 1 is true. The statement for the next number is true. So what does that do? I want to make sure you're clear on this. If, for example, the proof we're about to do, if I have a proof that just in general says that, hey, if you happen to know it's true for one, then it must be true for the next. That is, if you possess this, what does that tell you? That says, now this is a big if, right? This is a hypothetical statement, right? This is like, if this is true, then this is true. Well, what does that say? That says that, for example, if the statement holds for n equals 50, then it must be true for n equals 51. You see the kind of machinery you're going to build here. You're going to build a little proof that proves that no matter what, if you bring me a case that happens to be true, that's a big if, then my proof says that the next one must be true. Now do you see how this, at the beginning, as innocent as it sounds, sets off the chain reaction? If you've established that P of 1 is true, and you have a proof that given P of k is true, that P of k plus 1 is true, do you see how what's necessarily the case then? If P of 1 is true, what must be true? The statement must hold for n equals 2. You see how it's just going to light a fire as we go. Then if the statement happens to be true for n equals 2, well, it has to be true for n equals 3. And this proof acts like a set of dominoes, then hitting all of them out. Yeah.
Well, how do we prove 3? How do you?
Yeah, that's going to be, of course, the goal. Yeah, you're going to. Well, let's do it right now. Let's do it with this one right here. I'm tempted to see if I don't know if I ever recalibrate it, but this is a long enough proof that I think I'm going to want to do that for everybody's sake. Bear with me. So that's the thing we're going to prove. You still have it written down. And we've already verbally, but we'll do it right, we'll write it down, but we've all verbally already checked that the first case is true, haven't we? Easy. Okay. So let's just follow those steps and see if we can prove this. And you're right, the third step is kind of the big one. So, so first we just check that n equals 1 works. Right? So, is it true that the left-hand side, which is equal to 1, is equal to the right-hand side, which is equal to 1 squared? Yes. Next, assume that it's true for some n equals k, like some fixed n equals k. That is, just to be utterly clear, we assume what's true? 1 plus 3 plus 5 plus 2k minus 1 equals k squared. That is for some k. Does that make sense? Again, that's a big if. Is that necessarily true? Not at all. But if it's true, we're gonna produce a proof here. Hopefully we can fit it here. That if that happens to be true, then it must be true for k plus 1. You'll really like this. We now prove this is that 1 plus 3 plus 5 plus 2k minus 1. Well, what is the k plus 1 case look like? Well, it's just this statement with a k plus 1 plugged in, isn't it? Does that look like what the original statement would say if n was k plus 1? There's a reason I included this in here too. I'll show you that in a second here. But that is true. That is the previous term, isn't it? It does look similar to what's up here. In fact, it's the same sum as we had before, isn't it? Plus one more thing. It's the k plus 1 case, k plus first case. So let's try and prove this. The left-hand side is equal to we're trying to get it to look like the right-hand side, aren't we? We don't have much to work with, but we do have the things that appear above here to work with. So what would you like to do? What move would you like to make? Keeping in mind that we take this as if it's true. And the whole proof topples if it's not true. That's true. But if it's true, then what can you do here? Go ahead, Nadia.
Substitute k squared for all the terms like before.
Yeah, so that's what we'll do. We'll rewrite. Do you see that this piece here, she says, isn't that just k plus? Isn't that just k squared? There's a little more work to do, but you see how powerful using the assumption is. Again, this all hinges whether this assumption actually is true or not. But if it happens to be true, then it follows that the next case must be this, which is equal to, is that this come out to k plus 1 squared? Did you do it yet? 2k plus 2 minus 1. So what is that? Is that k plus 1 squared? Okay. So let's write a final statement. Therefore, one plus 3. I'm just going to restate the problem. Plus 2n minus 1 equals n squared for all natural numbers n. By induction, maybe, something like that. Okay. I think it's important to have some summary statement. You could even just say something like, therefore, the original result holds, or something. And you need to kind of wrap this up with a little bit of a bow, because ending here makes, you might be like, so did you actually prove it here? I know you proved that if it's true for k, then it must be true for k plus 1. But do you also then understand that what you've done is you've just now proved it for all n by this induction idea? Yeah.
Well, I was going to say, what would you say like by induction? Like, what does that even mean? Like, that you just like take that and apply it to anything?
Yeah, but that is, you've used this chain of logic, right?
Oh.
I'm just saying this is a little tiny proof that's like kind of inside the overall proof. I just want to make sure you understand that, like, really what you've done is you've actually proved now for all n, right? It's directing our attention, ourselves and our readers, to the fact that, like, okay, now consider all the evidence, right? Given this is true, and given that you've just made this syllogism, right? If A, then B, then now by induction you get every case. Okay. So this is how a proof by induction feels, a very classical feeling, a proof by induction. And it's a powerful proof. I want to caution you, I think we use the word induction in other classes with like a lowercase I. This is not like induction in the scientific sense. That's like a reasoning to the best hypothesis, right? So mathematical induction is actually deductive, right? There's nothing like, well, we're not sure. No, we're sure. This is like a deductive proof. There's no room for error. We've like done it. It's done. It's never to be overturned. Whereas that's not what we mean by induction in other cases. Maybe. So this is like with a capital I here. This is mathematical induction, which is actually a deductive piece of logic. Let's try one that's not arithmetic, that you couldn't prove maybe another way. But I do ask you to consider on these and all of these, how you might reason to this. Like, how did someone even come up with this to present to us and put on the board today? You know, it's not obvious that this would even be true at all. Whoa, what? 1/6 n times n. Apparently, we have a formula for the sum of the first n squared numbers. The sum of the first n perfect squares. That's cool, that's cool. So let's wade in here, see if we can do this one before we leave today. I think we can. So here you can see right away that it's actually not immediately clear that the first case is even true. We really do need to do the work of checking it. So go ahead and verify for n equals 1. That is it really true that 1 squared is equal to 1/6 times, I'm just going to do this in faith, but can someone just check that really is true? I'll cover the equality up until I really believe it. 1/6 times 1 times 2 times 3. Everyone okay with calling those equal? Okay, good. Next, assume true for, not for all n, but for some particular k value. That is, assume 1 squared plus 2 squared plus 3 squared, etc. plus k squared equals.
Mr. Chase, when we're using this proof, we have to like write the assume true for n plus k.
Yeah. Or something to that effect, right? Whatever, it doesn't have to be my words. I think I said something a little different on the previous one, but you get the idea. And then, I don't know, let's set us to work here doing this. Prove true for the next case, n equals k plus 1. That is, the thing we claim is going to be true, we'll see if we actually can prove it or not, is that if we plug a k plus 1 in, that also holds. Yeah? All right, well now let's do the work here. And then I think on this particular problem, you'll find that it feels similar to the last one a little bit, though the algebra gets a little messier. But we're going to use kind of the same trick here. Yeah, Annabelle?
Now, why do you have the k squared in there? Like, why wouldn't you take out because of the
Yeah, you just want like a triple dot in there?
Well, I thought you were just supposed to substitute like k plus 1 for k, like you did in the.
I did. It's just I just want to acknowledge, and can you acknowledge with us that the statement for k plus 1 includes the k squared as the previous term. And I think it's worth mentioning that so that it's more obvious that what we're about to do, like we did in the last one, is something that works, right? Like that we really do see that the previous result is like contained inside this result. So no, you don't have to write the k squared if you don't want. I think it's helpful though. So let's start with the left side, like we did before. It's not the only way to do it necessarily, but. And see if we can make it look like the right side of this. So using the same trick, Using the same trick. What are we going to write here? Yeah, we're going to use the inductive hypothesis. To make that substitution. Now, it's a little bit of work, but we do need to make it look like the right-hand side. By the way, this is just over here, 2k plus 3. This last thing, isn't it? Just want to make sure I'm making a note of that. Now, we're lazy mathematicians. One way to do it would be to multiply everything out, right? You get a cubic in k squared, collect like terms. You do it here maybe too, multiply all this out, and see that you get the same polynomial on both sides. Full credit. But can we be lazier? What do you see? What do you see in our target expression? What do you see here? Can we like get ourselves there quicker? Yeah, we can't. We can't eliminate something on both sides because it's not proven to be equal yet, right? We've had this conversation. Right? Do you have a suggestion? No, that was your suggestion. Yeah, do we have a name for putting it aside? Yeah, we could factor it out. Yeah. So I do think it's a really smart idea to factor out this k plus 1 because not just because that's a kind of fun algebraic thing to do, but because it's factored out in over there too, right? It's a really smart move. So now, in fact, speaking of smart moves, I might also just apply some wishful thinking. I'm also going to factor out a 1/6. You might think that's not possible, but
How did you do that
we
on
can,
the left side?
right over here. I don't know. Yeah, we'll see. I guess. So far, so good.
Wait,
I'm not done. But do you agree that this this times this is that?
yeah.
A k plus 1 coming out of there is a k plus 1 left over here. Well, what about the 1/6 though? What would I need here? All right, just verify that we have not changed the problem at all, that all we did is rewrite it using the distributive law. Do you see how close we are? We're just hoping that the thing in the big parentheses factors, once we simplify it, to k plus 1 times 2k plus 3, right? Do you feel it? Some of you are already there, maybe. I don't know. Let's see that it works. Was that 2k squared plus k plus 6k plus 6? So is that the right side? Is that factor as k plus 2, let's just wishful thinking, times 2k plus 3? Can someone check that that's actually true? Anyone? Be as lazy as possible is the moral of that story, right? And then, again, you need some final statement about the statement is true for all n, right? Sorry to run to develop that one, but does that make sense? Now, the only hesitation I give you, and I'll just show you some of the other ones, and you'll encounter one, I think, at least of this kind of the homework tonight, so I apologize that we didn't get to another kind. But there are lots of interesting ones we can prove that don't feel like this. Some of these are series ones, but I'd like to do, we'll do a couple more examples on Monday, of things that don't feel like this at all, but are still great candidates for induction. Lots of really interesting, here's some divisibility proofs, here's an inequality proof. So we'll do a couple more of a slightly different flavor on Monday.
Wait, oh, never mind.
Yeah. So
I thought we were going
yeah. So yeah, we'll have Monday to clean up a little bit, and Tuesday to review some more. All right, have a great weekend, guys. Do your best on homework 6 tonight. See you on Monday.